Hello, in this video I want to take a look at evaluating limits with something called the dividing out technique. So here we have the limit as x approaches -3 of the equation x squared plus x minus 6 divided by x plus 3. And that function, that rational function, I have included a graph of it off to the right. Something interesting about that graph is that it does not include any asymptotes as you might assume of a rational equation. You might assume something looking a little more like this in your rational equation. But there is none. It's just a straight boring line. However, there is something unique. We can see at x equals -3, there's this hole in the graph, and I've kind of emphasized it a little more in this graph. So essentially it's undefined at -3. There's a hole or a jump over in the graph. And as we analyze this limit, we're going to think a little more about that hole. So looking back at our limit, we know that when we do limits, we should first try direct substitution. That is always the first thing you should try and just see what happens. So if I plug in -3, what does happen? Well, I can first see I get a 0 in the denominator, and then on the top I have 9 plus -3, so that is 6. Minus 6 is 0. I have 0 divided by 0. And more importantly, I have 0 in the denominator, which means it's undefined there. So I don't know what the limit is. Okay, but I don't stop there. Because it is of this form, 0 over 0, we call that indeterminate. It is indeterminate because we don't know if this limit exists or not. But also because it's indeterminate, we can continue on and evaluate this in a different way. Because I have a polynomial function on the top and the bottom, I can factor this guy, and maybe something will cancel out that'll make my life easier. So I look at the top, two things that multiply to -6 and add to 1, and I get x plus 3, x minus 2. And then the bottom's already factored for me. Now here, I have the same thing on the top and the bottom, so just like any fraction, I can reduce those, and I now have the limit as x approaches -3 of x minus 2. I got rid of my denominator problem. Now I'm just looking at the limit of this new function, x minus 2. So I found this related function, and going into detail here, that is what I'm doing. I now found this related function, x minus 2, which is equivalent to my original in every aspect except for I eliminated that hole at x equals -3. Because if you think about graphing y equals x minus 2, that's a y-intercept at -2, slope of 1, all right, boom, and we have our graph. So it is that straight line we originally had, but I have now filled in at x equals -3, which means as far as finding the limit, I can do that. I can gain that information now. So we can go ahead and find that limit by direct substitution. So I plug in -3, and I see that my limit is -5. Back to the original graph, if I had the graph, I could have easily seen that the limit is in fact -5. Because graphically, you can see that from the left, it is approaching -5, and then from the right, it is also approaching the y value of -5, so it makes sense that our limit is in fact -5. Okay, I want to take another look at a limit where we can use that technique. So here we go, limit as x approaches -2 of x cubed plus 8 divided by x plus 2. Now if I plug in -2, because I always want to quickly try direct substitution, I see that once again, I get 0 over 0, so I have that indeterminate form, which means I should try that dividing out technique. So anytime I plug in and I get 0 over 0, I should look, do I have a couple polynomials that are easy to be factored? If so, we proceed with the dividing out technique, and we see what happens. So I try and factor the top, which we should recognize that that is a sum of cubes. And we know how to factor that as a plus b times a squared minus ab plus b squared. All right, so that means we go x plus 2 because 2 is the cube root of 8, and then x squared minus 2 times x plus 4, which is 2 squared, all over x plus 2. Hey, look at that, nice factoring, because my x plus 2's cancel, which that has just dealt with the problem child of x plus 2. So now as I write my new equation, x squared minus 2x plus 4, which again, to emphasize, that x squared minus 2x plus 4 is exactly the same as our original function in all points, except there is no longer a point of discontinuity, a hole in the graph, at -2. So I evaluate the limit by plugging in, direct substitution, and I end up with 4 plus 4 plus 4, which is 4 times 3, and that is 12. So we have our limit. All right, let's look at one more limit here. I have another rational equation with a quadratic on the top and the bottom. And when I plug in -4, I get 16 minus 28 plus 12 over 16 plus 8 minus 24. And we can see by some nice subtraction and addition that we once again have 0 over 0, that indeterminate. And then I see polynomials that look like they can be factored, so therefore I try and factor this and hope I can divide out and then find the limit. So this one we do have to factor both the top and the bottom, so I look for two things that multiply to 12 and add to 7. That would be 4 and 3. And on the bottom, multiply to -24 and add to -2, gives me x minus 6, x plus 4. Hey, what do you know? It worked out again. Okay, so those cancel out, leaving me the limit as x approaches -4 of x plus 3 over x minus 6. Put this one in just to emphasize it's okay, we still have a denominator. Nothing wrong with a denominator, they're good. But the problem was when I got a 0 in the denominator. And you'll see once I do direct substitution on this guy, I do not end up with a 0 down there. Instead I have -1 divided by -10, giving me a limit of 1/10. One more word of caution and advice for these. Whenever you have a rational function which has polynomials on top and bottom, you're probably going to end up using this dividing out technique. However, you can only use it if on your first try of direct substitution, you end up with the indeterminate 0 over 0. That's the only time you should try and use this dividing out technique. Otherwise, you'll run into some trouble.